clear what y is.
Okay, so, and what all we talked about is, for the most part, is measurable, actual measurable responses. Okay.
Right, we
That's
already
what
looked at
I'm-
continuous responses, that's correct.
Okay.
We won't be doing any logistic regression. Responses are continuously declining. Okay. So why we know about these things. And that's the- Okay, and then we've already, well, actually we considered more general models. The basic simple linear model is this. Just that's where E is. So for each observation, we see follows this. And the idea, and beta 1 is the slope parameter. Slope always has meaning no matter what the regression problem is. It's a change in y over the change in x. Specifically, beta 1 is the expected change in y if x increases by 1. Okay, so beta 1 is always has a definite meaning. And usually it's a parameter of interest. Again, the major assumption is you have independence between these two pieces of the model. It's a major assumption, and we check it with the residual plots. But if that's a true assumption, then the only connection between y and x is this slope. So there's always a natural model plus. And in this class we did it with confidence intervals or t-ratios. You could use one or the other. We looked at dispersion tests also. We have more than that. Okay, any questions on that? Well, then you just need a method of fitting, and you can, we talked about these squares. The only other one we talked about is called and this is a score, right? A of I. Actually, the only one we've used in this class is this one. Well, I should display this one.
What is your negative?
Use just between 0 and 1. It's just a square function. You see it's a fraction. Now you can't get the answer in closed form, but the computer doesn't care. And actually, at least the computer does least squares too. No one uses the closed form solutions anymore. Okay. But then, you know, we get the table of estimates, we get beta 1 half, standard errors. And then from that, you can do confidence intervals. Use Z or T. Or you could just do T ratios. T ratio, you just take this part and do that. So any question on the regression?
Page 98 in the book. I can just show you what it is. It's right above equation 7.5.21. I just couldn't figure out, I just didn't know where the numbers in determining the confidence intervals came from. So we took 2.06, but that came from the 1.89. Yeah.
Yeah, it looks like it's
Okay, so it is this thing, that's what I thought it should be, and then this thing here should be the standard error, or,
right, so.
okay, so, all right, good, well, then I knew what I was looking for, thank you.
I'm using sweet, I must have. Maybe I think. What page is that on?
That's 98.
We could go over some example, let's just go over some example. Let's just go through an example where we know the answers. We'll take normal errors, control not error later if you want to. And, I don't know, just take x, how about x1 15? So there's our x rate, and then let's just go out. Five times x rate. Similar. So it looks sort of linear rate. Like a pattern. But anyways, we'll proceed with the linear model. And then we'll just do all of it. You can save the bit, sometimes that helps. And again, you could do this with RGLM too. There's a summary of the fit. We're pretty close, right? The true beta was 5. Our estimate is 97. And certainly, here's the standard error. You multiply that by 1.96 or 2 for the moment. So it's what, like plus or minus 1.3 or something. So you certainly cover 5. 5 is in the confidence interval. So we have a successful confidence interval. We expect that 95% of the time. We could also do a t-ratio. T is 8.6. Think of it like a z, so you know you're going to reject each one. So it's high as. And this is like the R squared we talked about. This is less than 27. Okay. And this would be the test based on a dispersion function. It's 46 p-value 0 by 4 places. We'll differ a little bit from this. Okay. Again, you could put the fit on. You could do add line. And then you just have to put in the intercept. Any questions on the Russian one? Is that going to
Reduction and dispersion tests, that's our D,
D of
Reduc-
0 minus D beta hat
okay.
divided by top hat. Top hat, you can get,
You just
you
type
can
in
always
top
be
hat.
attributes. On the fit. And it tells you what you can get back with the all. Maybe you want top hat, or you want this. So you can just do fit. So you're. Well, no, the standard. Or standard deviations. So we're very close. It's not, don't estimate that, but it'll estimate something close to it. You could get this if you want. So what you really use, D of 0. Those are the sort. Okay, you can do a residual plot. You can do it, which is good in the law. I don't like that break there, but we saw it in data itself, so it's, I guess there's no pattern. It's just like you had maybe two things going on. So, I don't have any curvature in the middle. I'm not thinking of it. It's strange, you just have this good fit. Residual plots will drive you crazy. Often, if there's a pattern, it's, well, I shouldn't say often, but many times it's definite. You should do this before you do the inference, but once you look at this, I'm satisfied to do the inference. I don't see any curvature in it. I just see that gap. But I noticed the gap in the original scatter. Remember, you can do student types with those two. Let me see that. It's just our student. Then you could plot those versus what? Then you can put in these dimensionals. Edges for horizontal. Actually, they declared out those two lines. That's a weird. You know, if this was real data, you might investigate some of these points, especially these down here. See, when you had a gap like that, you would investigate it in real life, because maybe there is something else going on. You know, maybe these observations, after we thought about it for a while, these observations were taken like on Friday, and most of the data was taken on Thursday, Wednesday, Thursday. So maybe you have a day effect. Then you could go ahead and fit that. Okay? You have to have some reason for doing it. I mean, I have no reason whatsoever with the data we just made. But after looking at the student size residuals, if this is real data, you know, I would try to investigate these points, especially these low ones. It's like they don't belong. Any questions on that? Okay. Well, then we can continue with the lecture. We're talking about analysis of covariance. That is regression, but it's functional regression. So let's go back to the snake data. So this is the code we've been talking about for the snake data, right? So the snake data is in snake 2.0. Let's get the data and talk a little bit about it. Did that. I'm going to just. Okay, so this data, that's the response is how close you can get to the snake, right? So there's some people like number 26 must have touched the snake. And then the covariate is what was their initial? Like on observation 26, this guy initially could only get within 8 feet of the snake, whereas again, he was one of the treated. Now we have 4 groups, right? The first group is a placebo. Nothing is done to these people. They weren't treated for their snake phobia, and then the other 3 groups were treated. They were different treatments. Okay, that's important. What we're talking about. So again, in analysis of covariance, you have a covariate in this case. So again, in analysis of covariance, what we love to see is sort of when we plot the data, we get these parallel lines for groups. Right? Maybe that's a group 1, this is group 2. Then in that case, there's a distance between them, and it doesn't matter where you are in covariate space, it's about the same. That's your effect, right? That's like the difference in means or medians between the groups. Now, if they're not parallel, then you cannot do that, okay? Then you have this situation where, say, bigger is better, this is group 2, this is group 1. And group 2 is winning here, all right? 2 is the winner, but over here 1's. So it's like inconclusive. There's no overall effect. What you can do is just take certain values of x. These are often called pickup points, and you can do a confidence interval on that gap. It's just a difference in expected values of y given x. We're not going to talk about that in this class. But that's one thing you can do. So there's alternative. There's alternative. Procedures. Okay? Well, getting back to the snake data then, the way to think about it, the full model is this. This is heteroscedastic. It's the heteroscedastic slope. And you can actually think of the design matrix as this. You have, well, there's a couple ways of thinking about it. Maybe we should just do the increment. So there's an intercept, and then this would be treatment 2, right? This would be treatment 3, and this would be treatment 4. So this is group 4, group 3, group 2, group 4. Okay? Now this is the model you want. All the slopes are the same, you just have one covariate. But now you have these interactions, and that's exactly what they are. Okay, so we have what? This is beta 1, beta 2, beta 3, beta 4, beta 5, beta 6, beta 7. So then your first test is to test beta 5. I'll write in a separate constraints because there's 3 constraints. It's not one. That will be your first null hypothesis. And if this is true, you're going to go ahead and assume the same source. Then you're in this good case. So suppose we do this, suppose we go this direction. Okay, so we're going this direction. Then next hypotheses, I put some labels in these or whatever, would be what? The effects are the same. There's no treatment effect. The treatments were no good, or they were all the same. So there's no treatment effect. And what you might want to test then also is was the covariate important? Now, if you can't go down this route, so you can't, then what do? You're back to like pick a point or whatever. You can do overall tests. We'll talk a little bit about it. Then how do we test these hypotheses? We just fit full and reduced models. For instance, on this one, this would be the full design, right? But the reduced design is easy to pick out. It's just this piece. This would be the reduced. Or this hypothesis. So then you just, it would be D red minus D blue. Blue is always smaller. There's 3 constraints, and you just divide it by time. And how do we do that? We could actually do it by hand. using that dollar disc. But there's a package that does it, and in this class, that's what you would want to look for. You would want to look for a package that does it. So we didn't write an old wrapper that does it. This is code. And it says header. This is for the header production model, and it's second hypothesis of it. Let's just do that code. And C4 has 4 levels in this, and Y is the response, and X is the delivery. Question?
Are you doing the computer now?
Oh, that's why I have 2 screens. Why did you build this without 2 screens? So to understand code, what we do it, okay, header means header stochastic. And there's 4 levels, okay, 4 levels, 4 groups. And Y, this is actually the Y and the indicator grouped together. I don't know why I did that. Just do that, rewrite that. It just says you're testing for homogeneous slopes. This is H naught, homogeneous slopes, and the answer is no. The p-value is 0.001. So you reject H naught and you have heterostochastic slopes. And we looked at the pictures last time, and that's true, right? The slopes are not the same. So in a sense, you're done. This will test groups, but it's like an average, and I wouldn't do it. That's the trouble when you write a wrapper. It's like you stop thinking. Some people will test that. It's with the full module. Okay. So here you would reject it. So going back to our schematic, you can't go down, right? You can't. See, we're stuck. I reject it. Can't go down. Now, in this problem, you can always think. All right. It's nice. You know, the scientific way is you set up a hypothesis, you go out and gather data, and you test it. But once you have the data, you should look at other things too. And if you go back to those plots, it was just a placebo. The placebo was crazy, right? And it's tempting to kick out the placebo, and that's what I did. And we finished a good discussion on analysis. So I have all this is just getting the plot. It's right here, okay?
Let me switch over.
Well, it's this is an exclamation equals when it means not equal to 1. So I subset the data. I took out reverse treatment from the Y and the indicator really, and then the covariate too. So first of all, let's do this, the one we just did. Now we only have 3, C of 3. Watch. Subset of data. See here, I failed to reject H naught, the p-value is 0.45. And if you remember the pictures, that's true, right? These pictures. I guess they're not. But the P, if you remember the pictures, this should be true. They seem to be about this. We didn't have them on the same plot. A couple people yelled. But anyways, we tested it and we confirmed it, okay? Now the slopes are about the same, then I can go on. I don't want to use this one. I want to go on. Now I can drop down and go on, and I can test the group of that. And that's the second wrapper. Homogeneous slopes, okay? Now the slopes are behaving similarly, but the effects are not. There's real effects, right? The p-value, this is the group one, this is one hypothesis of interest. You have two constraints, two effects, and the p-value is 0.0003. So you would reject it if not, the groups are different. And then you might try to do some kind of comparisons. See which group is best. It also tests the covariate. The covariate is much needed, okay? The p-value is, 10 to the minus 7. So it's highly significant. And this is our final story of analysis of covariance, for today anyways. Now we're in the case of homogeneous slopes for the three treatments, right? And what if you didn't have the covariate? Well, you could do a one-way ANOVA, but we could also just do a Kruskal-Wallis, right? Suppose I didn't have the covariate around. Then this would be the Kruskal-Wallis test, right? The first variable is the response, and the second variable is the treatment indicator. And then you can just put in Kruskal.test. See, it's not significant. So if you do the Kruskal-Wallis test, it's not significant, okay? P-value is 16%. That's the power of the covariate. See, with the covariate, it's highly significant. With the covariate, we say there's a difference in treatments. And if I don't have the covariate, I can't say it. That's the adjusted analysis. Okay? That's what people do nowadays. I mean, that's what they call in the paper. They've adjusted analysis. They should be doing many more in life. I think we could eliminate a lot of the dumb testing we do. At least the schools, if we just did some good statistical analysis. Okay. Any questions on that? Okay, the last few minutes. I'm going to talk about the two-way analysis, and then from that we'll probably do block designs, and then we'll get near the end. My last talk, we have time. K-way analysis, but two-way would be not to talk about. And then we can talk about like the randomized block design, which is a special case. But in two-way analysis, you have two factors. In factor A, it's maybe A levels. Factor B is B levels. And we're going to set a cross design. It took a while to convince people to use cross designs. They used to do one thing at a time designs. So we're gonna set up a cross design. And there are certainly many examples. One we have is lifetime Y is lifetime number. And X is temperature. Where insulation. I think three, that is the 3 by 3. You could think of this as designs, and did many of these designs at NASA, right? Or NASA we haven't done for like the Marshall, Marshall Road thing running around Mars. Looks so young. So you want to know how long the motor lasts. I mean, they were very surprised on the first one, it lasted. It's still running. The first one's still running. It's still running. You collect the data this way, we just collect it in the grid, right, in your cells. Let's just do the 3 of them. We have 1, 2, 3, 1, 2, 3 levels, and then we just collect the data in cells, and then we can model in cells too. In fact, the full model in this case is our old friend one way and another way. So here, you have Y, I, J, K. This would be the Kth response. Level I, K. This is and then we just model this one. It has some mean, median, doesn't matter. We'll be looking at effects, so it doesn't matter if it's means or medians. So our full model we've already done, just the one window. But you have structure in this model, and at the moment, we don't have any structure, and that's what analysis variance does. It tries to discern structure. Right? Is A important? Is B important? Where's A and B in this model? It's not. Wrong. I don't even have to have, I could just string these out if I wanted to. So at the moment, I have no structure, and we'll put structure in the model. Nice structure. It's called the additive. Then we get scared that maybe we didn't soak up everything. So what's left is like information. We'll do that on Thursday. Okay, so it's not to approve, so spread out. Take your time on the quiz, it's not hard.